Okay, we're gonna do a little bit more with this material testing thing to get those little cement balls on there. I spent a little time after our lecture yesterday to put some stuff together, and there's a number of little interesting things that kept coming up as I was trying to do that. So I want to point those out. Okay, so let's just do a little review of that first, and we're gonna get to that. Just walk through this again. This is this microbial induced carbonate precipitation where you pump in the magic elixir and it creates cementation, as you see here between the grains. I love these pictures from these SEM scanning electron microscopes, like, because when you look at a grain of sand, it looks like the surface of the moon. I mean, there's so much detail in there. It's just incredible. Um, And here's the idea of putting a string of particles and then bonding them to the to the sand grains. This was called a cement chain model, and we're just doing a little example of this in 2D. And if you recall, we have a system like this. We wrote some code called make cement balls, where you gave the radius of the cement balls and it went to every single contact and it put two of them on each side so they're just touching. It then did a model clean to create the new contacts. And so the resulting system should have 5 contacts, 1 of them between the sand grains and 4 of them between the cement and sand grains. And we're assigning a contact bond model to those things, right? And I'm going to show you right away a little way that I can use the extra variable at the contacts so that I can make this plot to make sure that things are working right. We put in a contact bond model. It has 5 parameters. This was the little mathematical derivation we needed to do to figure out the location of this particle. So that's that. Now we want to make this plot to check out if this system is right. We want to make a plot that we're going to do the ball group. And we've already done that because remember, the group is going to be yellow for sand and gray for cement. And we did that because when the balls that we had, we said we put the group label sand on them. And for the new balls we created, the cement balls, we put the group label cement. And so that lets us see that system. But then I wanted to, it would be nice if we could somehow actually designate with different colors the different types of contacts here, the sand cement, as you see here, and the sand sand. So I'm going to show you how we did that. In words, we did 2 lines. We're using this extra variable. If you recall, the different PFC components, balls, contacts, walls, they can have associated with them data. They can have associated with them in any sort of data. And the way that that's associated is by using this thing called an extra slot, an extra variable. And it has slots 1, 2, 3, 4, all the way up to 128. And so what I'm going to do here, and that data it can be a text string, it can be a floating point number, it can be an integer, it can be a vector, okay, it can be any type that you can have for fish. So what I'm going to do is for the contacts that are between the sand grains, I'm going to set the extra variable and I'm going to just set a string in there. And the data is going to be a string that's going to say sand, sand. And then for the other guys, the other contacts, I'm going to set a string in there called sand, cement. So how do we do that? So let's take a look. This was the original one, cement chain elixir. And so this was what we worked through yesterday, where we create the 3 sand balls. And if I run that, I'm gonna get this plot. How did we get this plot? So Just one command. So here we wrote the thing that would make the cement balls, took a parameter, cement radius. We called the function, gave it a radius of 0.2 meters, created the contacts, and they're right here, okay? So what is this doing? Remember this range group sand match 2. That means both objects on each, the two objects on each side of the contact, if they're part of group sand, then that's the one. That's what this filter is going to do. And so for those guys, we're going to create this extra variable in slot 1, and we're going to put the string sand. And for the other guys, where you match sand on one side and cement group on the other side, we're going to put the extra thing called sand cement. And then the way we view that, let's just do this here. Call this Fred. And so again, let's just walk through this again. There's all the balls in the system. And then what we want to do is shape ball color by group, if you remember. And let's get those colors like they were before. So the sand ones will make yellow. Cement ones will make gray. That's what we saw before. Let's make the line thickness smaller. So there's our groups. And now we want to plot. And now this is data associated with contacts. So we're going to use the contact plot item. And what we're going to do is we're going to say shape sphere. And I got to make it a little bigger. We can see it right there. And then we're going to say color by. Now, what are we coloring by? Well, it's a text string. So it's a text value. It's an extra thing right here, extra. And then I can go through index 1, 2, 3. It's index 1. And so here we go. This is now that extra variable. And now I can see, oh, these are sand cement, the pink ones, and these are sand. So that's a very helpful thing to see what we've got and what we've done. And then we went through this thing and we said, let's write a new data file that's going to create a material, and then that's going to test that material, right? And so we said, we have to write a function, a data file called make material. We're going to tell it as parameters. We're going to have a concept of a material vessel. And we're going to create walls. We're going to make one of the walls be a platen, so we can then give it a velocity. And then we're going to be able to measure the force acting on the platen, divide that by the cross-sectional area. That's called sigma. We're going to write a fish function to do that, and we'll call that sigma y. To get the strain, we'll write a fish function epsilon y. The way we get the strain is we're going to look at the displacement, let's call it delta, of this platen and divide it by h. And that's going to be the strain. And then we can make a history where we plot this fish variable sigma y versus the other fish variable epsilon y. And that's where we got yesterday. And let's just see what that is. So then we go into cement chain make and test. That was the one from yesterday. And so we have this master data file. The idea being, you'll see this all over. That's like in a directory that does a bunch of complicated stuff. You just call master.dat and it does everything that needs to be done in the right order. So this make material, here's the parameters we decided to use to describe the system. There's the width and the height of the vessel, minimum and maximum ball radiuses, target porosity, density, and then Kn, because we're going to use the linear model. So that's the value of Kn we want. And this K ratio is the ratio of Kn over Ks. So therefore, if you know Kn and you know the K ratio, you can compute Ks. And this is what we typically do. You're going to find out that we typically do this because the overall macroscopic Young's modulus of our systems are going to be directly proportional to Kn. And we're going to find out that the Poisson ratio of our macroscopic systems are going to be related to this ratio of Kn over Ks. And we'll find out why mechanically later on. But that's why we typically do not just specify KS separately, we specify a KN and a K ratio. And then friction coefficient, right? And so if you remember making the material, this was our, right, we set up the contact model assignment table, and we say for all the ball-ball contacts, assign the specified values of KN, KS, and fric. And for the wall contacts, for the ball facet contacts, give the same values of KN and KS, but make it frictionless. We did a domain. We generated a box of walls. We deleted the top one. We created a new one that's called platen because we're going to use that later to do things to it. We use the ball distribute command in the same box as where the walls were. And here we just use one bin, and we give our min and our max, and we tell it what's the desired porosity. We give a density and a damping, and then we cycle 10 so that we have some cycles in there so that the solve has a system to work with. And remember, when we do the solve, so we get to this point and we have all these big overlaps. Now, what does this do? So it keeps setting their velocities every 10 steps back to 0, so we don't get guys blowing out of the walls, because this is a fictitious thing. This is just some strange algorithm we're doing to generate this. To make a specimen, you could, if you want it to be actually the most realistic, is you would take particles and just let them fall under gravity and build this thing up and then bond them together. That's going to be a relatively slow computational process, whereas if you do this and make them push apart, you can achieve the packed state much quicker. But that is an effect, right? And you guys who do lab tests know this better than me, but if you take sand and pour it into a specimen and then do a test, and if you take sand and you slam it down on the table a few times, it packs tighter, and it will have different material properties. So if it's important to resolve the behavior at that level, then you would have to mimic that same process, right? You could do that with PFC. You could drop particles, let them fall under gravity, get packed, and then you could essentially take the base here and apply a velocity that's like a pounding, right? Where it would go up and down, up and down, up and down, and then this system would respond and it would pack tighter. But we're not going to do that right now. We're just going to do this quick way. There we go. We get our packing. So there's our packed system. And now we saved it. We called it the material. So there's our save file. And of course, that save file is also in the directory. This is the directory we're working with. There it is. That just got created. Now we can go, we're done making the material. So we can go to the data file called test the material. And so here again, remember, we restore this. We need to give a platen velocity. In order to do that, we just set the wall. Which wall? The wall that has the name platen. We specify that y velocity as the platen velocity, and it's the y velocity, so we want to do negative. We put a positive number here. We're going to reset the displacements of the wall to 0. So it's sort of like, now we're ready to begin this test. Now we've established a reference location for that platen. Here's our sigma y function, right? So the sigma y is going to be right here. The total resultant force on the wall in the y direction. And we're going to switch the sign of that, and then we're going to divide by the area, which is going to simply be the width. That was our parameter of the size of the vessel, the width times 1 unit thickness. In order to call this function to get the force on a wall, we need to get a pointer, or what we call the address of the wall. So we're going to do that here and make it a global variable. And so this is a function wall.find. You give it the name of the wall, it returns the pointer to the wall. That's why I called this WP, wall pointer. And I did the global variable because now when I write the epsilon y function, I can use that variable in there as well. And so that's just going to be my delta y. It's the displacement in the y of that wall. And I take that divided by the height, right? And then the last things I do is I add these as histories of these fish variables. And I'll call it my sigma y, my epsilon y, and then I'm going to cycle. And what I did also is I created a new view called stress strain curve, and the only thing in there is this history. All right. So if I run this, here's my stress strain curve. I labeled it axial stress. And remember, I have a minus here because I'm using the continuum mechanics sign convention, which means that if stress is positive, it's tension. So I'm going to flip this sign. So minus the axial stress because I want to plot this in this direction, right? This is the typical way we plot stress strain data for geomechanical applications. And so let's see. Yeah, now what can we learn a little bit if we play around with this? Why does this here stress not start at 0? They're packed in here, and so there's already here it is. There's forces acting on that wall right from the beginning. And let's restore the material. There we go. Before the test, at the beginning of the test, they're already packed. Let's just see, what could we do? What if we rebuilt this material, but we put more balls in here? What do you think would happen to that initial stress? Higher stress. Let's see if that's actually true. So let's remember what this value was. Whoops. Let's run test material. All right. 2.9, 2.9 E4. 2.9 E4. When I make the material, let's change that porosity. Instead of 0.16, let's do 0.04. Now it's packed even tighter because now there's more balls in there to get that lower porosity. And now if I test the material, oh, what was the other one? 3.9. And now it's up to 9 E4. And also notice how it's nice and cleanly linear because it's already tightly packed. For the other case, it was kind of rearranging itself a little bit right from the beginning when we started to do the test. Now, let's shut this down. Now, these things I want to point out. Okay, so what we're trying to do is we're going to modify the make material so that we can actually now put those cement balls in there. So we want to use the function that we wrote, that function called make cement balls, and we want to use it to put those cement balls in there, right? So let's talk about this. So here's the new so what I did is I made a new directory for the whole process, and I called it cement chain make and test 2, right? And so let's open that one. And the first thing that we're going to see is I created a file called add cement, and this one is called .p2fis. And what is that? This is a data file that only contains the fish function. So I pulled out this from when we created it, right? And so now what I'm going to do when I do the make material, so here's the make material from before, okay? Except a couple things. I'm going to, at the end of building this thing, I'm going to say model save, and I'm going to give it a name, the material with no cement. And then I'm going to call in this file, which really is simply going to load in that fish function, because it's going to go through this file, fish define, there it defines the fish function, end of the function. Now that function exists inside of PFC, so I can call it. And now I'm calling it. Okay. And then I do a clean, and then we're going to talk about the few other things that we had to do. The other thing I did is when I built this material, I also I stick on the label sand to all the balls. I put them in group sand, okay? Because we're going to have to designate between sand balls and cement balls, if you remember, okay? So if I run this, let's see, what are we doing here? Make material, yeah, this is right. My view, there's our material. And now I can do the plot. I can do the ball group plot, and it's going to say ball group default equals sand. So there we go. We just have sand guys in there. Okay. Now let's get rid of this for the moment. So now make material. Next step. Program call. Now I got the function. Let's call this function. Make cement balls. Let's run it again. Oh, look at this. Let's zoom in. There are the cement balls, right? If you look on each side, here's a contact on each side. 1, 2. Here's another contact. 1, 2. Okay. Thing I realized right away, notice here, the cement balls are overlapping each other. Okay. Which I guess in principle means those guys are actually their cement that's fully filling that gap. Right. And so that was the first thing I found out. Notice how small, notice when I made the cement balls, we have to give the cement ball radius. So I went and made it as a function of the minimum radius of the sand, right? So if I make this bigger, what you're going to see, this is what I saw the first time I ran it. It looks all crazy because they get, so I would argue that this system is probably not very realistic. There's too much overlap between the cement for this scheme. So that's why I went back to 0.07. I ran it. This is kind of cool. You can watch these guys get created. Presto. Okay, so now we got the cement balls, but we're not done. Okay, so the other thing that I had to do is in the make material is I had to make, when I create the material, I don't want to create the linear contact model because I can't put bonding in that. So when I created the material here, I'm creating the linear C-bond material. That's the contact bond material. And if you recall, by default, it is not bonded and it has the same parameters, Kn, Ks, and fric. So this is now the linear C-bond material. Let's see if that's really what I have. So if I go in here and I create a contact plot item, and then I say color by model name, there we go, linear C-bond, active. Okay, so that's good. Well, group, there we go. Right, I got sand is yellow, cement is gray. Now, after I make the cement balls, I need to create this. We'll create the contacts that are in there. And now think about this system. I have 3 types of contacts in this thing. This gets a little bit complicated. I have sand contacts and I have cement contacts. So let's just call that sand and cement. And then down here, I have sand and cement. So there's all these possible permutations of possibilities, right? There's sand contacts. There's sand cement contacts. There's cement sand contacts, and there's cement contacts. Make sense, right? There's 2 things and there's 3 combinations because the sand cement and the cement sand are the same, all right? Which means that all those different types of contacts have to get dealt with, okay? So first of all, I just want to visualize them. So I'm going to use that same trick. I'm going to put the extra field on the contacts. And these are the guys that are the sand because they have sand on both sides. These are the cement because they have cement on both sides. And these are the cement. So let's see if we can visualize that. That made sense. And one other thing, when I added the cement, what I had to do is notice when I create the ball, instead of making it exactly the cement radius, I made it a tiny bit bigger because I needed to make sure that those guys actually were overlapping so that contacts got created. Okay. And the other thing I had to do is in this make cement balls, I actually only want to loop over the ball contacts, not the ball facet ones. And I can do that with this loop for each with this contact list for each local contact in the contact list, but this can take an optional parameter. So notice this is just going to be the list of the ball contacts. So there we go, visit all active ball contacts. So those things had to be changed in here to make this work. Okay. And so now let's see if those extra fields, let's see if we got the things we wanted. So let's look here. It's going to create those. So now we're going to use the contact plot item, but we're going to use this extra field 1. So holy smokes, what's going on here? Let's take a look at this. So cement is black. There's the cement. That looks good. Sand cement is blue, right? There we go. There's sand cement. That guy's also connected to that guy, right? And then sand is red. So it looks like it worked. That's pretty cool, isn't it? This is actually the bonding network of this system. This is a very complex system that we've just created here. Okay, we sort of have 2 levels you could kind of think of connectivity in here. So now we have all those contacts in there. So we have to give them properties to these existing contacts. And so again, when we give them properties, there are 3 types of possibilities that we have to handle depending on, right, if you're sand cement, or cement. This first one I commented out because by default, all the contacts that were ball were assigned these properties and they were assigned linear C bond. So I don't have to I don't have to redefine those. But for the new guys, for the sand cement and the cement, I have to give them properties. So, whoa, this is complicated. You can see, because right, there's different types of properties depending on what type of connection you are. So I just put in some numbers here, okay? But Kn, Ks, fric. So if this was a overall parameterized model, where these are the material properties, suddenly there's 6 more material properties, right? Then I had to bond them together. And now because they're bonded, I have to give a tensile strength and a shear strength. And that's what I'm doing here to the 3 types. And I'm just giving it effectively infinite strength. We're not going to screw around, and we don't have time to look at this and see how it responds. So if I do this, now they're created and they have strengths. Let's just verify that quickly. So turn this off. So the contacts should have strength. So if I use the contact plot item, I turn off all this other stuff, and I look at numeric value CB shear strength 1E20, right? So it looks like that worked. Get rid of that. Notice also how we're doing this all like step by step, right? And we're checking as we go by using the visualization. And here's a whole new thing. So not only do we have, now we have this whole set of contacts. There was a bunch of them that were new. They have to get properties. In addition, we have to tell the system what to do if new contacts form, right? What properties are they going to get? Because there will be potentially new contacts, right? If we squeeze this enough, those 2 surfaces might come into contact, right? Or those 2 surfaces. Remember, those guys Those are the cement guys, so they may come into contact, right? And so there's three types of situations we have to handle of what to do if new contacts form. And so that's what we're doing here. We're using the contact model assignment table, but instead of the way this thing works, instead of saying default, here's default. By default, if the type is ball, do this. But the way that this contact model assignment table works is it's an ordered thing. So there's basically default types, but then there could also be other entries in this table. And so what this is saying is that for the guys who are sand, that's what this range group is doing. For the guys who are sand, add this as a slot in the CMAT. That's why it says CMAT add. And so we're adding 3 new slots that are going to get handled depending on what type of contact it is. And the way the CMAT works is it starts on the bottom and it sees if any of these slots are satisfied and then it uses them. If none of these slots are satisfied for a new contact, it goes back up and uses the default stuff. And so notice what I'm simply going to do is for any new contacts that form, I'm going to just use the linear contact model. That's the simplest thing. I'm going to assume that new contacts that form, I'm not going to later go and bond them. So that's why I'm using the linear model. And again, I'm just giving properties here. So again, if this was a fully parameterized system, there would be now 9, there's 6 additional properties, and here there's 9 more additional properties, because to fully specify what your model is doing, all that information needs to be conveyed. Okay. So you can see there's a lot of details here. So now if I run this thing, I'm going to get the material with cement. I get both of them. So I have this funky looking material. If I go to the material, no cement, all that stuff is gone. With cement, there we go, because it has, okay. So now I can test this, right? And the testing thing is exactly the same, right? The only difference is I restore the material with cement, and now I do the test on it, right? So let's do the test. And my view, and now I just need to cycle. Whoops, just a second. Oh, I don't have the walls on. There we go. There's my system. Look at the force chains. Let's look at something else first. Let's look at this. We're going to plot each ball with a displacement. We're going to draw it as an arrow and show the displacement vector. So what we should see when we start pushing down, there should be eventually the whole system should start moving down. So let's see if that's what happens. 1, 2, 3, go. There we go. It's pushing down. Notice the high value of displacement in red, 50 millimeters. The low ones are on the bottom. They're near 0, right? They're not going down at all compared to that, right? I can color by scale by magnitude. There's your magnitude, right? Now you can see there's not much here because we didn't move the bottom, right? So that seems to make sense. I look at the force chains. Now this is crazy complicated. I'm gonna zoom in here. See if I can find a good one. It's hard to see. Let me cycle it some more. You can see how it's pushing down because it's getting squeezed from above. The whole thing is moving down. There's my stress strain curve. Can you see this right here? Those red lines. For this particular location, the sand grains are getting pushed apart in a shearing type fashion. There's a shear force between them because this line is not center to center. And that's then being balanced. That's causing tension right here, right? Because there's two contacts, one on this side, one on that side. And look at it's in tension. Look at, I zoom in. Isn't that cool? It's in tension. It's getting pulled in tension. This guy is not getting pulled in tension. This guy's getting squeezed. This guy's getting squeezed, right? reset to model extent. And there we go. So we have a very, very complicated system now, right? And obviously we could then get all kinds of interesting stuff if we wanted to look at this and how it starts to break and all that kind of stuff. Last question. What is going on with this curve? Why is it not just a nice, clean, straight angled curve? What's happening here, I'm squeezing this, and what I did is I just instantaneously started moving this. It used to be 0, and suddenly it was 1e to the minus 2, which means that there was actually a compression wave that goes through here and bounces back, and that's causing a ringing in the system because it's this compression wave. It's like moving down, and then it goes down a little bit, comes back, goes down, and it's a pretty minor thing, but that is happening. If I were to run this again, I haven't done this, so my plant velocity is huge there. 1, let's make it be 0.1 and run this thing and look at the stress strain curve. Now I got to cycle more. And there's still a little bit of ringing, but it's at a much, much lower amplitude, okay? And so this is another issue about, what's happening when you're loading this. Ideally, you could have some fancy business where you don't just instantaneously apply the velocity. You might slowly ramp it up. Then you would minimize this. We're going to find that this doesn't really have much of an effect unless this is super huge. This is just a minor thing. It's probably not affecting any breakages, and it's breakages that we care about. And so when we run our real tests, we're going to say, oh, look, it's not breaking, so it probably doesn't matter. And the overall stress strain curve is going to be the same for the different velocities unless we get really, really high. And notice how that ringing has damped out. And now we're getting a nice, clean, straight curve. And there we are. Okay. And with that, the only last thing I wanted to show, and this will just be a couple slides, is we did there's an example in there of a shear box in 2D. And so now you can understand how this was all done. This pink guy is considered a single wall. And that guy has a servo control acting on him to push down, to maintain a certain confinement. This black guy is the bottom of the box. And what we do is we keep the bottom fixed and we just move the pink guy at a fixed velocity across. So we have an applied confinement and we move this at a velocity. And this is granular material in here, right? So this is a shear box test. And while we run this, we monitor the displacement of this pink wall. So that's the applied displacement in the shear box. And then we monitor the dilation of this wall, and we monitor the force that is the shear force that's needed, right? So when you run this for a little bit, so you can see the difference. What do you notice about the force change between the initial state and after I've started pushing it? They're at an angle now. This is the forces, right? Somehow there's a shear force that has to get applied to this wall. It's because the material rearranges, the force chains rearrange. You can kind of see the big trend right here where this is now starting to push back. And so this would be the type of things we're monitoring. These are just histories, the X and the Y displacement of that top wall. And so we're forcing the wall to move with the velocity in the X, but the Y is free. So therefore, it's actually moving up. It's dilating. That's just naturally happening. And then if we look at this, then our servo is trying to maintain a constant normal force. And then here's the shear force. And we haven't run this for enough, but you will reach a steady state shear force. And this, of course, is a super crude model with not very many particles. So yeah, there's all kinds of people have done work with these type of systems with PFC. And, and of course, the shear force you get will be a function of the normal force. If you add more normal force, the shear force will get higher, right? And of course, the behavior of this is highly dependent on the friction coefficient and on the shape of these grains, right? And a similar thing could be for a rock test. People also do shear box tests on rock. That would be the same thing, except this material now would end up getting constructed as a bonded system, and you would apply this. And then the last thing, sometimes people then also, as we'll see, we have the ability to build a bonded system and to put in a joint that goes across these things, and we can use special contact model there so that that bumpiness is removed, and we can control the properties of that joint. So people might make this a bonded system, put a joint across, and now do a shear box on a test on a rock joint, right? And so that's another thing that people would often would do with something like this. Okay. So that's we've now concluded what we're doing related to fish.